Okay, thank you very much. So yeah, I'd like to begin by thanking the organisers for the opportunity to speak and take part in this really nice conference. So today I'm going to talk about Brownian half-plane excursions, conformal loop ensembles and critical Liouville quantum gravity. And this is all based on a forthcoming joint work with Yuhan Aru, Nina Holden, who spoke yesterday, and Shin Sun. Yeah, this is a work which will hopefully be appearing on the archive very soon. Okay, so before I go into details, the main aim of today's talk is going to be to describe a correspondence, which is one of the key results of this forthcoming paper, between two objects. The object on the left-hand side, which is a Brownian half-plane excursion, and the two objects on the right-hand side, which combine to give something called CLE decorated Liouville quantum gravity. Okay, so I'm going to describe what these objects actually are very shortly, but the main message I want to get across in this talk is that we are able to construct a correspondence or a coupling between the objects on the right, which are very intrinsically interesting for many reasons, but a priori potentially quite complicated to understand, and the object on the left, which is hopefully much more familiar to people. And what I want to try and get across is how actually through this correspondence we can encode many of the properties of interest of the object on the right-hand side by properties of the object on the left-hand side, which is, as I said, hopefully a bit more familiar to people. Okay, yeah, so it's all going to be, I'm going to keep it very high level, and I'm going to try and describe our result without perhaps stating anything fully mathematically rigorous, but I really hope you'll at least get an idea of our result and some kind of flavour of what's going on, and at least some food for thought. Okay, so let's begin defining the object. So I'll start with the Brownian half-plane excursion, which hopefully people are quite familiar with, or at least very familiar with a planar Brownian motion. So a Brownian half-plane excursion, what I mean by this is going to be a random path living in the upper half plane of the complex plane, which starts at the point 1, 0 and ends at the point 0, 0. So what it is it's just a planar Brownian motion. So that's just two independent Brownian motions, one for each coordinate, which starts at the point 1, 0 and is conditioned to remain in the upper half plane until it first exits at the origin. So that conditioning needs a bit of justification, because of course if you start a planar Brownian motion on the x-axis, it will immediately go below the x-axis. So conditioning on this event is actually conditioning on an event of measure 0, but we can make sense of this conditioning via a limiting procedure, and then we refer to this process as planar Brownian motion started at the point 1, 0 and conditioned to exit the upper half plane at the origin. Another way you can think about it is that, okay, so this process, it has a certain duration, which is random. It has some explicit law. And if we condition on the duration, then the x and the y coordinates are just two independent Brownian processes. So the x coordinate is a Brownian bridge from 1 to 0 with the specified time duration, and the y coordinate is a Brownian excursion staying positive from 0 to 0, again with the specified duration. All right, so that's the Brownian half-plane excursion. And one point which is going to be quite relevant in today's talk that I want to now try and emphasize a little bit is that in this Brownian half-plane excursion, because the y coordinate is just a linear Brownian excursion, we actually have a natural branching process which is embedded inside the process, right? Because as I hope that lots of people know, if you have a linear Brownian excursion, then from this you can build something called the Brownian CRT. So if you have your excursion, which maybe looks something like this illustration in the bottom left-hand side of the slide, then you can put an equivalence relation on this by identifying points which can kind of see each other under the excursion, and then you can generate the Brownian CRT. So in this Brownian half-plane excursion, there is naturally embedded a certain branching process. Okay, so can you still see my slides now?
Yes, yes.
Okay, I had it on full screen, but I found it really distracting that I couldn't see anything apart from
Okay,
that.
yeah.
So
No, it's fine like this as well. It's not a problem.
Okay, good. Right, so that's the Brownian half-plane excursion. So now I need to define what the objects on the right-hand side of my first slide are. And I'll start with the conformal loop ensemble. Okay, so I'll refer to this as CLE from now on. And in fact, this is a family of objects which are indexed by a parameter kappa. And for this talk, in fact, I'll in the end be interested in actually one value of kappa. But for now, we'll assume that kappa is a real number between 0 and 4. Okay, so what CLE kappa is, all you need to know about it for the purposes of this talk is that it's a random collection of disjoint simple loops in the disk. So you see this very nice simulation by David Wilson on the right-hand side. Really what this is like this little illustration in the top right-hand corner of the slide. Okay, so it really is a collection of loops which have simple boundaries and don't touch one another, but in the real simulation, it looks a lot more complicated. And the reason it looks a lot more complicated is just because the boundaries of these loops are actually fractal curves. They're like SLE type curves, like Nina talked about in her talk yesterday. And also the loops, although they do not touch one another, are like really, really close to touching one another. Okay, so this really is a random collection of disjoint simple loops in the disk, and these were introduced by Wendelin Werner and Scott Sheffield around about 10 years ago. And these are like loop analogues of the SLE curves that Nina was talking about in her talk yesterday morning. All right, so these are very central objects in random planar geometry. And one reason why they're so important is because they're actually characterized as the only possible collections of random disjoint simple loops that satisfy two very natural properties, which are conformal invariance and a certain spatial Markovian property. So we don't really need to know about this for this talk, but I do need to talk a little bit about conformal invariance. So what this means in this context is that if I have a CLE in the unit disk of the complex plane and I apply a conformal map from the unit disk to itself, then if I look at the law of the image of the CLE, this will actually have exactly the same law as the CLE itself. And what that means in particular is that via the Riemann mapping theorem, you can actually define CLE inside any simply connected domain. And in particular, if you have a CLE, so a picture like this with all these disjoint loops, then each CLE loop itself bounds a domain, which is a simply connected domain. So we can actually define CLE inside each of the CLE loops. And this gives a very natural way to define something which is, I'll call a nested CLE, which is going to be an infinitely nested sequence of loops. And what you do is you start with a simple CLE, then inside each loop, you just sample an independent further CLE, and then you keep going. Okay, so you have like an infinitely nested, iterated CLE in the unit disk. Okay. Right, so that's what CLE is. And another reason why it's important is, and which is very closely tied to the fact that it's characterized by these two properties, is that it's a conjectured and in some cases proved scaling limit of interfaces in critical statistical physics models. So for example, if you take an Ising model on some lattice approximation to the disk and you have the right boundary conditions, then the interfaces between positive and negative spins in the models is known to converge to CLE3. Okay. Right, and in this talk, in fact, I'll be interested in one particular value of kappa, which is the value kappa equals 4. So remember I said the range of kappa, where you have this simple, these simple disjoint loops is when kappa is between 0 and 4. Kappa equals 4 is clearly on one of the ends of those regions. And as such, it's a kind of critical value because it's a transition point where the behavior of CLE changes. So in fact, you can define CLE kappa for kappa bigger than 4, but in that case, the loops will actually have boundaries which touch themselves, and they will all touch one another as well. And kappa equals 4 is like the transition point where the loops stop being simple. Okay, so in the case kappa equals 4, the loops are simple and they are disjoint, but kind of barely so. So the boundaries get really close to touching themselves and lots of the loops get very close to one another. So the case kappa equals 4, which is going to be the case of interest in this talk, and indeed this is the case that's simulated on the right hand side, is a kind of special critical point. Right, so that's CLE4, and yeah, now I need to define the other object, which is critical Liouville quantum gravity. Okay, and we heard a little bit about this in the talks yesterday from Nina and also from Remy Rode. So what this again is a family of objects, but now instead of being a family of random loop configurations, it's a family of random measures which are defined in some simply connected domain from a Gaussian free field. Okay, so very roughly speaking, what these are is they're measures which have density given by the exponential of a Gaussian free field. Okay, and as we was discussed yesterday morning, and as I'm sure everyone knows well, the Gaussian free field is a very rough object. In particular, it's only defined as a random distribution. It doesn't take values of points. This means that actually a priori it doesn't make any sense to kind of exponentiate the Gaussian free field and use it as a density of some measure with respect to Lebesgue measure. But nonetheless, you can kind of take this formal definition and you can make sense of it. So if you have a Gaussian free field on some planar domain, say it's called H, then via a regularization procedure or an approximation procedure, you can make sense of these Liouville quantum gravity measures, which I've denoted by mu gamma here, which formally speaking have a density exponential of gamma times the free field with respect to Lebesgue measure. And what these measures allow you to do is to, in the end, give sense to areas of certain regions in your planar domain where the Gaussian free field is living, and also to measure lengths of curves. And that's what we're going to use it for in this talk. Okay. And yeah, so one reason, there are many reasons why this is important, and we've seen it pop up already in the conference. Another reason, one particular reason why people are interested in these measures is because they're conjectured to be related to the scaling limits of random planar maps. So I won't say anything really about what random planar maps are, but essentially they are probabilistic objects obtained by gluing together huge numbers of polygonal faces according to some weighting. And these give you some discrete metric spaces and also some discrete measures if you consider counting measures on the faces. And the conjecture is if you can formally embed such objects into a planar domain in a natural way and consider these, the resulting measures, then these will actually converge in an appropriate scaling limit to LQG measures. And this is largely a conjecture for most values of gamma. So certain weightings on random planar maps are conjectured to give rise to gamma Liouville quantum gravity measures in the scaling limit. And actually, this has been proved in one very special case by Nina Holden and Shin Sun. Okay, and again, just like for CLE, I'm going to be interested in one very specific value of gamma, and that's when gamma equals 2. And again, this is a critical parameter. So I didn't say it before, but in fact, this process of making sense of these Liouville quantum gravity measures turns out to be nice to do when gamma is between 0 and 2 and strictly less than 2. So there's a kind of sensible approximation procedure which gives something nice in the end. And gamma equals 2 is again a kind of transition point where the behavior changes. So in fact, you actually can't define alluvial quantum gravity measure with gamma equals 2 in the same way that you can define the measures when gamma is strictly less than 2, but via a renormalization procedure, you can make sense of what I'll call a critical alluvial quantum gravity measure. So yeah, in this talk, I'll be interested in this critical case where the behavior of the measure is actually quite different to the behavior of the subcritical measures for people who know about those guys. So finally, they're the two objects, if you remember my first slide, they're the two objects on the right-hand side, but I want to combine them. So I just need to explain how I'm going to combine them to give something called CLE decorated alluvial quantum gravity. And the way I combine them is basically in the simplest possible way. So I take a CLE4 in the disk, or in general, I can take a CLE kappa defined on the unit disk of the complex plane. And then I also take an independent Gaussian free field on the unit disk. And from that, I define the alluvial quantum gravity measures. So on the same disk, I have defined a CLE and an independent Gaussian free field and resulting alluvial quantum gravity measure. All right, so I've taken the objects and I've combined them basically in the simplest possible way. I've coupled them in a simple way. And this is actually a kind of natural way to couple them, because in fact, it's conjectured that if you take certain random planar maps, which are decorated with loop configurations, and the probability of sampling a certain random planar map together with a loop configuration is weighted by the loop configuration. So this is a discrete object that combines loops and random planar maps in a way that they're not independent. The conjecture is that in the scaling limit, these things actually decouple, and you do get CLE together with an independent alluvial quantum gravity measure. And this is the case when the parameters of CLE and LQG are related by kappa equals gamma squared. Okay, but today I'm just going to be interested in the case where kappa is equal to 4 and gamma is equal to 2. So, and I'll call this CLE4 decorated critical alluvial quantum gravity. And in fact, to be a little bit more specific, I want to work with a kind of very special case of critical alluvial quantum gravity, which I'll call a critical quantum disk. So all I mean by that is that you take, when you take a specific variant of the Gaussian free field to define your LQG measures. And this is a very natural variant to take because it's actually the one that's conjectured to give the alluvial quantum gravity measures that arise as scaling limits of certain finite volume random planar maps. Okay, but don't worry about that too much. I mean, I just take a specific form of the Gaussian free field on the unit disk, and I consider its critical alluvial quantum gravity measures. And on top of that, I have an independent CLE4. And that's the picture that I want to explain has a correspondence with a Brownian half-plane excursion. Okay, but before I do that, I need to introduce just one more object, which is just related to the CLE4. And this is something called the Uniform CLE4 Exploration Process, which was introduced by Hao Wu and Wendelin Werner. Okay, so what I'm going to describe is basically a dynamic way to construct a CLE4 in the unit disk from a Poisson point process of so-called SLE4 bubbles. Okay, so the SLE4 bubble measure is just an infinite measure on simple rooted loops whose boundaries look locally like SLE4 curves. Okay, so something like these blue and green guys, but a lot more fractal looking in real life. Okay, so I have an infinite measure on these bubbles, and if I have such a measure, I can take a Poisson point process of these bubbles. And basically, you can use this Poisson point process to kind of grow or construct dynamically a CLE4 just by adding in the bubbles one by one in the order they appear in some kind of conformal way. Okay, and when you do this, in the end, the bubbles that you added in, the images of those after this conformal adding in procedure will be the CLE4 loops. Okay, so to be more precise, what do I mean by kind of conformally adding in, and why is this a uniform exploration? Well, basically, this adding in procedure goes as follows. So this is a bit of a simplification, but suppose at some time you've discovered some amount of your CLE4, Okay, and then at that point, you'll have drawn a load of loops in the domain, and there'll be some remaining to be explored domain. Okay, and then suppose you have, the next bubble. Okay, that doesn't really make sense, but you have another bubble in your sequence that you want to add in. Okay, and what you do is you just do this. You take your bubble, which is rooted. It's a simple rooted bubble, and you put the root at a point chosen uniformly on the boundary of the unit disk. Okay. And then you can formally map that whole picture into the remaining to be explored domain of what you've discovered so far. And what that results in is, inside your picture, you add in another bubble, and the point where this bubble is rooted on the boundary is chosen from harmonic measure on the boundary of the to be explored domain. So, like you can see a very simple illustration in this picture. Suppose we've explored explored to the point where we've just discovered this one blue bubble, and we want to add in this green bubble. What we do is we root this green bubble at a uniform point on the boundary, and then we can formally map this whole picture, so the second bubble down, into the picture with the first bubble to give a picture with two bubbles. Okay, and we carry on like that. So in the end, we build up a collection which builds a CLE4. Okay. So what might not make total sense in what I just said, and it shouldn't, is when I was talking about the remaining to be explored domain. So that only really makes sense if I've specified a target point in the domain, because, in my exploration procedure, when I draw a loop or something, then I cut the domain into some number of simply connected components, say 2. And to say which one is the remaining to be explored domain, what I need to do is I need to specify, for example, specify a target point. That will determine which is the remaining to be explored domain. It will be the one containing the target point. Okay, so in fact, what I just described gives you a way to construct a branch of a CLE4 exploration procedure towards a specific target point. Okay, but this has a very nice property called target invariance that I can actually take. If I take 2 target points, then I can couple the explorations towards those 2 target points such that they coincide exactly until the first time that the 2 points are separated by the loops in the exploration. And after that time, they just evolve independently. So what that means is I can actually take a dense set of target points in the unit disk and target, simultaneously define these exploration paths towards each point, such that the branching property I just described holds simultaneously for all pairs of points. So the upshot of this is that I can actually define a branching CLE4 exploration procedure towards all points in the unit disk simultaneously, or towards all rational points. So what I get is a dynamic branching process which builds the entire nested CLE4. And it actually builds the nested loops, because in a certain branch, if I discover a loop containing the target point, I will continue the process inside that loop. So this branching procedure builds the entire nested CLE4. Right. So there's a bit of a subtle point which I need to briefly mention, which is, what I've now described is a branching exploration, or a branching dynamic way of constructing a CLE4. So that's, a coupling of this exploration procedure together with the CLE4 that it generates. Okay, but what I would really like to think, the point of view I would really like to take is that I have a CLE4, and associated with it, I have this exploration procedure. So a natural question to ask is, in the coupling of the CLE4 exploration and the actual CLE4 that it generates, is the exploration process actually a deterministic function of the loops themselves? And we very strongly believe that this is the case, but in fact, there's still a bit of work to be done to have this written up rigorously in the literature. So from now on, I would really like to be able to say we have a CLE4 and we have this deterministic exploration procedure associated with it, but I can't rigorously say that. So whenever I say we have a CLE4, I actually want to say we have a CLE4 together with an associated exploration procedure. All right, but that's the CLE4 in its exploration. And there's one tiny extra thing which I need to introduce, which is, in fact, as we'll see in just a second, in the coupling with the Brownian half-plane excursion, it's going to be important to have a way of ordering the branches in this exploration procedure. And in fact, when you look at this branching exploration process, there isn't a kind of intrinsic way to do that. And it turns out, in the context of the coupling, the right way to define an order on the branches in this branching exploration is just whenever you reach a branch point to toss an independent fair coin to decide which of the branches comes first. Okay, so I want to add basically a little bit of extra randomness into this picture of the CLE4 in exploration by ordering branches by flipping a coin whenever 2 points are disconnected by the exploration. Right, so now finally, as promised, I can get on to describing the correspondence with the Brownian half-plane excursion. So what I described on the previous slide is, that if we have a CLE4, we can use an exploration procedure of this CLE4 to give an order, a branching structure on points in the disk or on loops that we discover in the CLE4. And also, if we allow some additional randomness through these coin tosses, we can give an order to the branches. And what this branching structure is going to correspond to in the coupling with the Brownian half-plane excursion is really going to be this branching structure that I mentioned at the beginning that is embedded via the CRT, which is defined by the y coordinate. Okay, but if I actually want to have a coupling with the Brownian half-plane excursion, I need something else. I need something to actually tell me what the x and the y coordinates in the half-plane excursion are doing. Okay, and this is where the Liouville quantum gravity measure comes into play. So remember, I have a CLE4 and I also have on the same unit disk an independent Gaussian free field variant together, a Gaussian free field variant, which gives me a way via Liouville quantum gravity measures to measure areas of regions and lengths of curves. So it's very natural then to consider, when I think about this branching exploration, the observables given by just the boundary lengths and the areas of the loops that I discover along the branches. So I really mean the quantum boundary lengths and areas. So the boundary lengths and areas as measured by this independent Gaussian free field. Okay. So once I have all that, the entire picture I have now from the CLE decorated LQG, plus the exploration procedure, plus these independent coin tosses, is, I have an ordered branching structure, and along each branch, I have a sequence of observables, which are the Liouville quantum gravity boundary lengths and the Liouville quantum gravity areas of the loops that I discover. And in fact, it turns out that there's an analogous thing in the Brownian half-plane excursion, as recently made very precise in a work of Elie Idacon and William de Silva. So in fact, if you look at a Brownian half-plane excursion, you can do something which is to cut the Brownian half-plane excursion at a certain height. So like you can see these thin horizontal lines in the picture. And if you do that, then you can consider the sub-excursions that the Brownian half-plane excursion makes above that height. So at the bottom one, you can see there's 3 sub-excursions, and the top one, you can see there's 3 different sub-excursions. Okay. And associated with each of these sub-excursions above a given height is 2 natural quantities. So the duration of the duration of the sub-excursion, so just the time it takes for the Brownian path to traverse it, and also its displacement, so the difference between the left and the right endpoints of the excursion. And in fact, you also see that there's, a natural branching structure. You can see it from this process of looking at sub-excursions above heights is actually the same branching structure induced by the y-coordinate CRT. As you increase the height, you see that sub-excursions will split and they will die. So there's a natural branching structure encoded by or embedded in the Brownian half-plane excursion. And in this branching structure, there's a kind of obvious order to the branches just defined by the chronology of the Brownian path itself. So one sub-excursion will come before another if the Brownian path traversed that one first. So exactly the same as what I just described for the CLE4 and the Liouville quantum gravity, from your Brownian half-plane excursion, you can yeah, you can define a branching structure, an ordered branching structure, where along each branch you have a sequence of observables given by the displacements and the durations of these sub-excursions. Okay, and in fact, this entire process was recently described completely explicitly as a growth fragmentation process by Ellie Idacon and William De Silva. So they were able to describe the law of this process embedded in the Brownian half-plane excursion completely explicitly as a growth fragmentation. All right, so basically our result, which I'm now going to present in a very non-rigorous way, is that we can construct a coupling between a CLE4 decorated critical Liouville quantum gravity disk plus an exploration procedure of the CLE4, if you don't take it for granted that that's a measurable function of the CLE4 itself, plus a load of independent coin tosses, so that the things I described on the previous slide do actually map to one another. And this is, yeah, about as precisely as I'm going to state our result. So when the paper actually appears on the archive, if you're interested, you can look for a kind of a very precise version. Okay, so our result is there exists a coupling so that the following correspondences hold. So in your CLE4 decorated critical LQG disk, together with the exploration and the coin tosses, you have a branching structure and an order on the branches, and what that's going to correspond to in the Brownian half-plane excursion is the branching structure in the associated CRT, or equivalently the branching structure you get if you look at sub-excursions above height and increase the height with the natural order defined by the chronology of the Brownian path. Okay, and importantly, two observables you can look at in the CLE4 decorated critical LQG disk are the boundary lengths of discovered disks and the areas of discovered disks as measured, sorry, when I say disks, I should probably say loops, as measured by the underlying Gaussian free field. These are going to correspond in the Brownian half-plane excursion picture to the displacements of sub-excursions above heights and the durations of the sub-excursions above heights. Okay. And in fact, there are a few other correspondences that I will very briefly mention. So in our CLE4 picture, because we have nested loops, then we have a notion of parity of nesting. You know, a loop can be even if it's surrounded by an even number of loops, or odd if it's surrounded by an odd number of loops. Okay, and in fact, there's an analogous thing in the Brownian half-plane excursion. Actually, if you look at sub-excursions above heights, these actually come associated with a sign, and that depends on whether the left or the right endpoint of the excursion was visited first or second by the Brownian path. And it turns out that these signs actually map to the parity of nesting in the CLE loop picture. So excursions above heights will correspond to CLE loops, and their signs will actually correspond to these parity of nesting. Another thing to briefly mention is a kind of very natural observable in the Brownian half-plane excursion is the height. So I mentioned, you know, we want to increase the height to see this branching structure. What this corresponds to in the CLE4 disk is actually a way to measure some kind of quantum distance from the boundary of points in the disk or loops in the CLE4. So that's an interesting observable that we can define on the right-hand side from this on the left-hand side from this correspondence with the Brownian half-plane excursion. And finally, just to briefly mention, what does, you know, the time parameterization of the Brownian path correspond to? This really corresponds to a kind of global time parameterization of our ordered CLE4 exploration, where the time parameterization is by quantum area. Okay, but I won't dwell on that. I should also, I want to mention or emphasize that, in fact, in this coupling, if we have the CLE4 plus its exploration, plus the Liouville quantum gravity measure, plus the coin tosses, then actually we can reconstruct in a explicit way the Brownian excursion. Okay, so the Brownian excursion is a deterministic function of all the stuff, and we can describe exactly how to build it. Right. And that's it. So I'm running short of time, so I will just put up these questions, which I think we can discuss in the discussion. So I just mentioned that the Brownian excursion is encoded by the CLE plus all this extra stuff. There's an obvious question, which isn't so easy to describe, which is whether you can go in the other direction. Another thing to mention is I mentioned that we can use the height of the Brownian half-plane excursion to define a distance of loops to the boundary in our CLE4 picture. And for those who know about it, there's also another way, a very natural way of defining distance of loops from the boundary, which was introduced by Sheffield, Wu, and Watson. And it's an interesting question to work out if there's an explicit link between those, and we think they are. There is. And the third question is about scaling limit results related to random planar maps. And I know that this is going to be talked about a little bit by the discussants, so I just will put this up here. There are basically two candidates, and we can come back to this slide in the discussion later. Okay. So I will say in just 2 seconds, the idea of the proof, for those who know about it, is to take a kind of degenerate scaling limit of the result of Duplantier, Miller, Sheffield on the mating of trees, which gives a way to describe subcritical Liouville quantum gravity in terms of correlated Brownian motions. But in fact, in their picture, everything degenerates when you approach the critical regime, and so we need to do renormalization in all different kinds of directions in order to get something non-degenerate in the limit. So I will stop there, and I'm very sorry for ignoring all the questions in the chat. Thank you very much for listening.
Thank you very much. I think we will go directly to the discussion. That's by Sarai Hernández-Torres. So could you please share your screen? Yeah, perfect. You're still muted.
1 second.
There, okay.
Like usually my iPad works well, but not today. So just give me a second. I have a backup plan. Okay, good. I think that you can see my slides.
Perfect. Go ahead.
Well, I want to thank Ellen for the very nice talk, and also the organizers for having this nice format of SPDs and friends. So before I start, I want to clarify that I don't work in conformal random geometry, but I'm more like a friend of conformal random geometry. It appears as a I work in other dimensions, but it's like the motivation of let's see what people is able to prove in 2 dimensions. We try to take this as a reference for what are the results that we are aiming in other dimensions. So my plan for today is I'm going to stick on a quite basic level on what is like kind of the global context of Ellen's and her collaborators' work, and how it relates to a 3-dimensional case, if possible. So let's start with kind of a beautiful main idea on all this, and this is these encodings of trees. So this is very well known, that if we have a tree like the one I have on the left, we can encode it with a real function by just taking its contours. So we consider a particle that is starting in the root, and it explores our tree from as the arrows indicate. So this shows it gives us this contour function, gives us the function on the right, and the same. Well, we can do the same for this continuous versions of the tree. So this is also very well known that the Brownian continuum random tree is encoded by this Brownian excursion. So and this is on the real line. So what is beautiful is that our convergence, on uniform convergence of real functions, corresponds to this Gromov-Hausdorff convergence of trees. So if, let's say, our discrete tree on the upper right part, this one, is a Galton-Watson tree, large, let's say that with a fixed condition to have fixed progeny P children, then the corresponding contour function will converge weakly to Brownian motion. And then means that in our space of trees, these large Galton-Watson trees converge to the continuum CRT in the with respect to the Gromov-Hausdorff convergence. So this is the best of the worlds, and kind of what I want to say today is that what Ellen and her collaborators do is to pushing these ideas to, well, further away. So then we go our next step, which is now we're going to encode these decorated maps that we have been talking about during yesterday and during Ellen's talk. So here I'm doing something a little bit more simple, which is a spanning tree decorated planar map. So planar map is this graph that is embedded on the plane with the edges. And by a decoration, it means that I have some, well, a spanning tree that is indicated here on green. And the law of, if I take a random planar map that is decorated as a spanning tree, the probability that I get a particular random planar map is proportional to the number of spanning trees. So if we take some other model in the statistical mechanics, we are going to take these probabilities proportional to the corresponding partition function. But in this case, the partition function is simple. It's just a number of spanning trees associated to this planar map. And we have a bijection, and now to walk in set 2 in the upper, well, in the positive quadrant. So for a planar map with n edges, we have a walk of 2n steps. And well, here, these images are taken from this survey on mating of trees for random planar maps and legal quantum gravity, which is very nice. Let me just tell you a little bit what goes for this bijection. So the first step that we have to do in this case of spanning tree decorated planar maps is, well, we already have a spanning tree, and now we are going to identify the dual of that spanning tree. So, well, this lives in the dual. It means that this spanning tree has, this dual spanning tree has vertices that correspond to the faces of our map. So remember that the exterior is also face. So I have a vertex here and all these other vertices. And well, the edges of this dual spanning tree correspond to the places where the green spanning tree does not pass by. So here I have my spanning tree, and for the ones that are in blue, it means that the spanning tree doesn't occupy those edges. Then I have an edge in the dual. So the tree on orange is the dual. And here I emphasize this construction because this is something very special in 2 dimensions. We don't have something like that in 3 dimensions. And even if you want to understand the structures, well, you can define what would be the dual of a tree embedded on a 3-dimensional space, but the object that you obtain is not more simple than that. I mean, it's not as beautiful as in the 2-dimensional case where the dual of a tree is again a tree. So there has been some attempts to understand what would be the dual of these structures in the 3-dimensional case by Matthew Kalle, his students and collaborators, but it's not clear how to go ahead on that. But here we can do it. So now we have 2 trees, the spanning tree and the dual of the spanning tree. And to obtain the last step of this bijection, and well, unfortunately I cannot draw it, is we consider the contour function between the dual and the tree. So this is called the piano curve, and this is the curve that is just in between the spanning tree in green and its dual in orange. So this is a contour function and encodes both trees. And here, there's also another step missing. And well, now you have your contour function, and how does this contour function specify a walk on this positive quadrant? And well, I didn't draw it because it would involve to have more lines, but essentially we can draw a quadrangulation from our planar map. And this quadrangulation is going to subdivide our vertices in triangles. And when we look at this contour function between the tree and its dual, it's going to cross these triangles, and we can assign a rule that if it crosses the triangle for the first time in the quadrangulation, then it's a step in a certain direction. So we have here 4 directions in the walks and 4 ways that we can cross these triangles that I didn't draw but correspond to a quadrangulation, and that defines our bijection. But here, kind of the main idea that I want to emphasize is that we have, well, the main ingredient is this 2 trees, the spanning tree and its dual, and that we encode both by taking the Peano curve between them. So this is the Newlin bijection. The next step in our journey is, well, now we go to a little bit more complicated and interesting statistics mechanics model, which is the critical random cluster model with parameter Q that decorates a random planar map. So in this case, Scott Sheffield defined hamburger cheeseburger bijection between these decorated random planar maps. And now, well, again, walk on this positive quadrant, but in this case, it's non-Markovian. In this case, it's non-Markovian. And here you have the issue that you no longer have a tree and its dual, well, a tree in the beginning. So, but in this bijection, you can define in a canonical way what would correspond a tree and its dual. So essentially, you get the pair, and this non-Markovian walk defines the contour functions of these pairs of trees. So, well, for time's sake, I won't go into details of this hamburger cheeseburger bijection, but it's essentially the next step of this more simple Newlin bijection. And if we go even further, then we have the mating of trees theory. So here on the upper part, we have these discrete bijections between walks and decorated random planar maps. And what we have now is the equivalent, but in the continuum. So as Ellen explained, these objects are, well, they converge to the CLE4 decorated with Liouville quantum gravity. And here I'm sticking to this regime where parameter kappa is between 0 and 4, and the parameter gamma of the Liouville quantum gravity is between 0 and 2. So Duplantier, Miller, and Sheffield define a lot of tools to make sense of what would be the equivalent of having these 2 trees that specify a correlated Brownian excursion and correspond to this CLE4 that decorates a Liouville quantum gravity. What is interesting here is that if you understand, well, we can understand the convergence of these walks to their corresponding Brownian excursions, and this defines convergence for these random decorated random planar maps to the decorated Liouville quantum gravity. So here, this is a situation that is different from the tree case, because in the trees, our convergence corresponded to the Gromov-Hauser convergence. And this is something different. This is called the pianosphere convergence, and it's its own thing. It's not like stronger, neither weaker than the Gromov-Hauser convergence. It essentially says that if we are looking at these pairs of trees on the discrete, this pair of three converges to this CRT pair that corresponds to these Liouville quantum gravity structures. So, well, it's a deep result. And this is where, Ellen and her collaborators' work comes in, because we can understand this as the critical case for this mating of trees. So you can think that this is a coupling between these correlated Brownian excursions and these decorated Liouville quantum gravities. But here we have a restriction of the parameters. They are below the critical dimension, both for CLE4, kappa, CLE kappa, and the Liouville quantum gravity with parameter gamma. So here they take the parameter kappa to be equal to 4, and this is the critical Liouville quantum gravity. So it's a special case just on the object that that they are considering. And here, what is expected is that when you take kappa converging to 4, then this correlated to the Brownian excursion converged to the Brownian half-plane excursion. But what is really happening is that they go directly to look at these objects and they build this correspondence that is a coupling. And for the last minutes of this presentation, I want to talk about why this is good, what is the power of the mating trees approach, and why it's interesting to have these constructions in these different cases. And for this, I want to talk about what I do in 3 dimensions. So this is the result that we got for the scaling limit of uniform spanning trees in 3 dimensions. And as you can see in this slide, this is formulated in a very general context that is valid in all dimensions. We have our uniform spanning tree with a metric and a measure and embedding, but you could define it in the same way in 2 dimensions. And here in this context, we were able to prove tightness and convergence at this moment in this particular sequence. And when I present this result, I usually refer to what is known in 2 dimensions. And well, I also phrase these statements in this very general that is possible in 2 dimensions to present, which corresponds to the formulation in the work of Martin Barlow, David Croydon, and Takashi Kumagai. So in that paper, in this framework, they were able to prove tightness, but the convergence comes from a slightly later result from Nina Holden and Shinson. And this is not formulated in this context. This is something that they got from this mating of trees approach. So this is where they can take the whole power of the 2-dimensional case. So what they did is to understand the mating of trees, but now on a Euclidean space. So that's something that has its merit, that they are not working just on this Liouville quantum gravity regime, but they are able to relate it to what is your uniform spanning tree drawn on set 2. And what they study is, here I have this uniform spanning tree U and its dual tree U prime, and what you have in between is this piano curve. So it's very similar to this set of problems that I have discussed today. And what they are able to understand is this convergence of the piano curve in strongnesses, so including the parametrization. Then it's just a corollary to obtain the convergence of the uniform spanning tree in the scaling limit with respect to the Gromov-Hausdorff-Prokhorov topology. This is just a consequence of using some general result for convergence of random trees. And since they understand very well what is the scaling limit of the contour function, it's done. And in the context of mating trees, you can say that this mating of trees topology that corresponds to these Euclidean trees, the uniform spanning tree converges to SLE8, because the SLE8 is the continuous curve that corresponds to the contour function of the scaling limit. And this is all. And perhaps we still have a few minutes, because I want to ask Ellen about these scaling limits in her case. So what would be the best result that they would be able to prove? And there's another 2 questions, but I think that the first one is the one I'm most interested in, and perhaps it's also interesting to other participants.
Right, so yeah, thank you so much for the really nice point of view on this. For the scaling limits, yeah, I can answer very quickly. If you wouldn't mind going back to your slide on that, because that was actually better than my slide. Yeah, so there's one scaling limit that one could try and prove, in the context of these FK decorated random planar maps. So very briefly, yeah, you have this bijection that was described with a non-Markovian walk on the quadrant, and this makes sense for Q for positive Q. Okay, and what Sheffield proved is that this walk converges to a correlated 2D Brownian excursion in a quadrant, and it turns out that for Q less than 4, the correlation is non-trivial, but for Q bigger than or equal to 4, the correlation is 1, and you just get one single Brownian motion. So what happens when Q is like very close to 4, but just below, is you get this very correlated 2D Brownian excursion. Okay, so if you look at that limit, the Brownian excursion in the limit, you can then do an affine transformation and take a limit as Q tends to 4, which gives you a Brownian half plane excursion. But the natural question is, actually, can you kind of skip this two-step process? Can you go straight from your non-Markovian walk in the case Q equals 4, do a different renormalization to what Sheffield does in his paper, so that you don't get something trivial in the scaling, you don't get just one Brownian motion in the scaling limit, do a different normalization and actually get a Brownian half plane excursion in the scaling limit. So the problem is that at the moment, the actual renormalization, the scaling you need to do isn't even known.
Yeah, so essentially what you want to do is,
this is like an analog of the pianosphere convergence in the critical case.
Right, to draw another arrow from
exactly.
the top non-Markovian walk to the Brownian half plane, and that would induce the critical pianosphere convergence corresponding here.
Yeah.
And of course, is this something that are you planning to pursue, or is it like, I don't know?
I would love to pursue it. It seems hard to me, but yeah, it would be a very nice thing if we can make progress.
But it seems within reach after this work.
And of course, you say, what's the best possible convergence you could hope for? Of course, you would like to, have some way of embedding your random planar map and show that the loops converge to CLE loops, and the induced metric converges to some kind of critical Liouville quantum gravity metric. But that is like miles off, because although I was talking about this critical Liouville quantum gravity, at the moment we only have a way to make sense of critical LQG measures. In fact, we don't even know how to define a metric associated with these measures in the continuum.
Good. Yeah. Well, thank you very much. We'll stop sharing.
Okay, so thanks a lot to both of you. I think we can also open up for other questions from the audience, if there are any. I thought there was a lot of questions in the chat. I don't know if all.
So there's a new question in the chat, which I think most of the questions I tried to answer, but there's a new one which is a very good question. I can answer that or try to answer that.
Yes. Do you want to read it as well?
Yeah, so it says, the Brownian half-plane excursion sounds like gluing a Brownian bridge with a Brownian excursion. Mating of trees sounds like gluing two Brownian excursions. Are their relationships to LQG essentially very similar from this point of view? So, yeah, you're right. There is definitely an analogy going on there. And basically, what I said very briefly is that our proof actually works by taking this mating of trees and renormalizing everything in order to get a limit as you approach the critical regime. But there are many things which really degenerate, and so the picture is quite different in a lot of ways in the critical case. So, for example, in the subcritical case, you can think about gluing these CRTs and you have a path that snakes between them. And in the continuum picture, this is this thing called space filling SLE kappa. And it turns out, and that's a continuous space filling curve. It turns out actually in the critical case, this curve completely degenerates. It's no longer, you can still define an analogous ordering on points, which is basically built from the CLE exploration that I described and the coin tosses, but it completely degenerates. You no longer have a space filling SLE4, as it's not a continuous curve at all. It's just a completely random ordering of the points. Another thing is, you know, one of the key results of Duplantier Miller Sheffield is that you have this Brownian, you have these correlated Brownian motions on the one hand, and you have your CLE decorated LQG on the other hand. And in their result, the two things are measurable functions of one another. So you can go in one direction and the other direction without any additional randomness. In our case, you really need some additional randomness. So to get from the CLE and the critical LQG to the Brownian half-plane excursion, you really need these coin tosses, to extra additional coin tosses, some additional randomness to reconstruct the Brownian half-plane excursion. In the other direction, we know that you do need some additional randomness, but we can't describe it very explicitly at the moment. So there's lots of similarities, but also lots of differences. Yeah.
Oh, so now there's a new question in the chat.
There are also recent results using TUT embeddings for SLE. Could they be used for CLE as well? Yeah, so that's a very good question. So I really don't know what's feasible to do in terms of random planar maps, critical random planar maps, or random planar maps which should in principle correspond to critical Liouville quantum gravity. Like, people have started doing work on this, but there hasn't been that much developed, and I haven't really thought about it in great detail so far. So I imagine there's probably, you know, at the moment I'm still even thinking that these kind of weak pianosphere type convergence results, if we could think of an analog of them, are already very hard. So getting some kind of embedding results seems even harder, but they're all, you know, interesting questions, and in principle you should be able to do something. It's just, I wouldn't like to say that I could do it.